Welcome to Next Gen Manufacturing. You know, we see all this incredible technology around us, from jet engines to super-fast race cars. But have you ever stopped to think about how we actually make the stuff they're made of? Today, we're diving into the massive and kind of hidden challenge of how you shape the unmachinable.
And that's really the core question, isn't it? We see these amazing feats of engineering, but we almost never think about just how hard it is to cut, drill, and shape the materials that make them possible. Well, the answer, it's all about what they're made of. So our story really kicks off with a whole class of materials that have totally changed the game in modern engineering. We're talking about polymer composites. They are, without a doubt, the unsung heroes behind so much of today's high-performance tech. So, what are these things exactly? Well, think of it like a super advanced version of papier-mâché. Seriously. You've got this soft, moldable polymer resin that's kind of like the glue, and then you reinforce it with these incredibly strong but lightweight fibers. What you get is this amazing hybrid material that has the best of both worlds. And that combination is precisely why they are such a huge deal. Composites are way lighter and often a lot stronger than metals like aluminum or steel. This makes them absolutely critical for industries like aerospace, where every single gram counts, and for high-performance cars, where that strength-to-weight ratio is everything. They let engineers build these wild, complex, aerodynamic shapes that you just couldn't make with old-school materials.
Okay, but here's the catch, and it's a big one. The very things that make composites so incredible also make them an absolute nightmare to work with. You can't just grab a standard drill bit, go to town on the stuff, and expect it to turn out okay. It just doesn't work that way.
The whole challenge really boils down to two big issues. The first one is called heterogeneity. It just means you're trying to cut two totally different materials at the exact same time. A soft, gummy resin and these super hard, brittle fibers. Just imagine trying to get a perfect, clean slice through a cake that has layers of soft sponge and then layers of hard, crunchy candy. It's a mess, right? That's the problem. The second issue is anisotropy, which just means the material is stronger in one direction than another, all depending on how those fibers are lined up.
And when you try to just brute force it with the wrong tools, this is the kind of disaster you get. You get delamination, where the layers literally start peeling apart like an onion. You get fiber pullout, where the tool just rips the fibers out instead of cutting them. And because this stuff doesn't conduct heat well, all that friction can cause thermal degradation. You're actually burning the material. It's just a complete mess that ruins the strength and precision of the part.
You know, this quote right here just perfectly captures how wild this problem gets. When you're trying to machine something like a remid fiber, you probably know it as Kevlar. The fibers don't cut cleanly at all. Instead, they create this fluffy aspect. It's so bad that it can literally close a hole right back up after you pull the drill bit out. It's crazy. So, for years, engineers just tried to solve this problem with the tools they already had, but it was this constant uphill battle. It basically turned into a tools arms race, just trying to keep up with these new materials.
First, they started with just standard high-speed steel tools. But nope, the abrasive fibers in the composites would just shred them almost instantly. Okay, so the next step was carbide, which is a lot tougher and lasted longer. But even that wasn't enough. For really high-precision jobs or big production runs, the industry had to move all the way up to diamond-tip tools, the hardest and by far the most expensive option out there. All that just to get a decent cut.
But here's the fundamental issue. It didn't matter how hard the tool was, because conventional machining is designed to cut metal and create nice, clean little chips. That whole process is just fundamentally at odds with how composites are built. So instead of a clean cut, you just get dust, intense friction, and a whole lot of damaging heat. A totally new approach was needed.
Which brings us to the million-dollar question that the next generation of manufacturing had to answer. If a harder, sharper blade wasn't the solution, then what was?
Well, the big breakthrough didn't come from a better blade at all. It came from completely rethinking what cutting even means, using two of the most basic forces in nature, water and light. And just look at this comparison. It really shows you what an incredible leap forward this was. Conventional tools, tons of heat damage. A water jet, it's a cold cut, so there's none of that. Old methods create all this dust and gunk. A water jet washes it away, while a laser just vaporizes it into thin air. And maybe the biggest deal of all, tool wear basically becomes a non-issue. It's a total paradigm shift. So let's meet the two heroes of this story, abrasive water jet cutting and laser cutting. See, these methods don't rely on brute force and friction. Instead, they use focused energy with an unbelievable amount of precision. To really get a sense of the power we're talking about with a water jet, just look at this number, 4,000 bar. That's the pressure. It's a stream of water, usually mixed with a gritty material, moving at supersonic speeds. To put that in perspective, that is hundreds of times more powerful than a firefighter's hose, all focused on a point smaller than the head of a pin. It just slices right through the material, with no heat, no stress, and no damage.
And then you've got laser cutting, which is almost like something out of science fiction. It's a totally non-contact process. A super-focused beam of light heats up the material so fast that it just instantly vaporizes. Poof! There's no physical tool, which means no tool wear, no dust, and absolutely no mechanical stress on the part. You're just left with a perfectly clean, precise cut.
So this is all really cool technology, right? But what's the big picture here? Why does this huge shift from mechanical force to focused energy actually matter so much?
Well, it matters because this is what the future of making things actually looks like. It means we can create parts that are completely damage-free, so we're preserving the full strength of these incredible new materials. It means we get ultra-precise cuts, we don't have to worry about expensive tools wearing out, and we can machine these insanely complex shapes that were just impossible before. This is what unlocks the true potential of these materials.
You know, this whole story of machining the unmachinable, it's not just about composites. It's really a preview of what's coming next. And it leaves us with this really important question to think about. As we keep inventing smarter and stronger materials, what other brand new ways of making things will we have to invent right alongside them? Thanks for joining us.